In this lecture, I will continue our exploration of the emergence of quantum mechanics. In the last class, we discussed the blackbody radiation problem and how the classical Rayleigh-Jeans model failed to predict the observed spectrum, resulting in the so-called ultraviolet catastrophe. To resolve the problem, Max Planck introduced a revolutionary assumption in 1900. Unlike the classical model, where an oscillator's energy could take any continuous value, resulting in E equals kBt, Planck proposed that energy levels are discrete and quantized. He stated that the energy can only exist in integer multiples of a fundamental unit, expressed as E equals nh nu, where h is a new constant now known as Planck's constant. Using the Maxwell-Boltzmann distribution, the probability p sub n of an oscillator occupying the nth energy state is given by the exponential fraction shown on the slide. Consequently, the average energy E is no longer simply kBt, but must be calculated as a weighted sum over these discrete energy states. Now, let us calculate average energy of discrete energy state. The denominator is the sum over all states of the Boltzmann factor, e to the negative nh nu over kBt. We use the formula for geometric series, which tells us that the sum over x to the n from 0 to infinity is 1 over 1 minus x for absolute value of x less than 1. Applying this to our denominator, we get the closed form expression, 1 over 1 minus e to the negative h nu over kBt. Next, we focus on the numerator, denoted by s, which is the sum over all states weighted by nh nu. Explicitly, this sum is written as h nu e to the negative h nu over kBt plus 2h nu e to the negative 2h nu over kBt plus 3h nu e to the negative 3h nu over kBt plus so on. We then multiply s by e to the negative h nu over kBt to obtain a related series. E to the negative h nu over kBt s equals h nu e to the negative 2h nu over kBt plus 2h nu e to the negative 3h nu over kBt plus 3h nu e to the negative 4h nu over kBt plus so on. Subtracting this series from s, the left-hand side becomes 1 minus e to the negative h nu over kBt s. On the right-hand side, the subtraction leaves us with h nu e to the negative h nu over kBt plus h nu e to the negative 2h nu over kBt plus so on, which is a geometric series. Summing this series, we get h nu e to the negative h nu over kBt divided by 1 minus e to the negative h nu over kBt. And finally, h nu divided by e to the h nu over kBt minus 1. Now, we can get the average energy from the denominator and numerator we calculated. The average E is S divided by 1 over 1 minus e to the minus h nu over kBt, and S times 1 minus e to the minus h nu over kBt. Then, E becomes h nu over e to the h nu over kBt minus 1. Next, we look at the energy density, U of nu t d nu, which is given by multiplying the density of states, 8 pi nu squared over c cubed, by this average energy. The expression becomes 8 pi h nu cubed over c cubed times 1 over e to the h nu over kBt minus 1 d nu. Now, to express this in terms of wavelength rather than frequency, we use the relation nu equals c over lambda and convert the differential accordingly. This gives u of lambda t d lambda equals u of nu t times the absolute value of d nu over d lambda, where d nu over d lambda is minus c over lambda squared. Substituting and simplifying, the energy density in the wavelength domain becomes u of lambda t d lambda equals 8 pi hc over lambda to the fifth times 1 over e to the hc over lambda kBt minus 1 d lambda. This final formula describes the spectral energy density of blackbody radiation depending on wavelength and temperature, completing Planck's model. Let's verify how Planck's formula elegantly resolves the ultraviolet catastrophe. First, consider the limit of large wavelengths. Lambda approaches infinity. Using the Taylor expansion for the exponential function, e to the x approximately equals 1 plus x, the minus 1 cancels out, and Planck's equation reduces exactly to 8 pi kBt to lambda to the fourth, which is identical to the classical Rayleigh-Jeans model. Second, and most importantly, let's look at the small wavelength limit. Lambda approaches 0. As lambda gets very small, the exponential term in the denominator becomes dominant and grows infinitely large. Because this term is in the denominator, the entire energy density, U of lambda t, drops and safely approaches 0 as lambda approaches 0. The ultraviolet catastrophe is completely resolved. This equation perfectly matched the experimental blackbody radiation curves at all wavelengths, beautifully bridging the gap that classical mechanics couldn't cross. Before we move further, let's consider the power flux emitted from a blackbody. This slide shows how we relate the internal energy density, U of nu and t, inside the cavity to the actual power flux, I of nu and t, measured outside the small hole. We already know that the energy density is defined as energy per unit volume, and the intensity is then defined as energy per area divided by time. Imagine we have a cavity with radiation inside, and at the base there is a tiny hole with area dA through which energy escapes. We analyze a small volume element dV, located at a distance r and angle theta from this hole. To find the total energy in a small volume element dV, we multiply the energy density by dV. Expressing dV in spherical coordinates, it becomes r squared sine theta dr d theta d phi. Next, we consider the projected area through which energy escapes, which depends on the angle theta. The projected area is given by dA cosine theta, taking into account the inclination angle. We then compute the fraction of the total solid angle subtended by the small volume element at distance r, expressed as dA cosine theta divided by 4 pi r squared. Combining these quantities, the energy dE that emerges through a small hole from volume element dV is calculated by multiplying the energy density by the volume, the solid angle fraction, and geometric factors related to the spherical coordinates. We then relate the energy flowing through the hole per unit time and area to the intensity, expressed as I of nu t d nu equals dE over dA dt. Next, we substitute the expression for dE and perform integration over all relevant parameters. For the azimuthal angle phi, the integral over the full range from 0 to 2 pi gives a factor of 2 pi. For the radial direction, we integrate from 0 to c dt, since the electromagnetic wave propagates through space at speed c. For the polar angle theta, we evaluate the definite integral from 0 to pi over 2 of sine theta cosine theta d theta, which evaluates to 1/2. Combining all integrals and geometric factors leads to the factor c over 4 multiplying the energy density, yielding the final relation. I of nu t equals c over 4 u of nu t. This relation succinctly connects the intensity measured through the hole with the energy density inside the cavity. Now, let's find the wavelength at which the power reaches its maximum. Using the relationship between energy density and intensity, we can clearly see the formula that connects these two quantities. Since the spectrum has a single peak, we can locate this maximum by differentiating the intensity with respect to frequency. The derivative consists of two parts. The first term comes from differentiating the numerator, 3 nu squared over e to the nu h kBt minus 1, and the second term arises from differentiating the denominator, nu cubed h over kBt times e to the nu h kBt over the quantity e to the nu h kBt minus 1 squared. Setting the derivative to 0 gives the condition for finding the maximum.
To simplify the equation, we multiply both sides by h over kBt squared times e to the nu h kBt minus 1 squared. Next, we introduce a substitution variable x equals h nu max over kBt, which helps simplify the expression. Using this substitution, the equation reduces to an implicit form involving x and exponential functions. 3x squared e to the x minus 1 minus x cubed e to the x equals 0. This transcendental equation can be rearranged into a simpler expression. 3 times 1 minus e to the negative x equals x. By plotting both sides of this equation, we can find the non-zero numerical solution, which is approximately x equals 2.82. Using this result, we then express the peak frequency nu max in terms of temperature T. This leads directly to Wien's displacement law.
Finally, let us find the total power emitted per unit area, P over A, as the integral over all frequencies of the spectral intensity, I of nu, T. We rewrite the integral by substituting terms and grouping factors for easier handling. Introducing the dimensionless variable x, defined as x equals h nu over kBt, simplifies the integral. With this substitution, the integral becomes an integration over x, involving the function x cubed over e to the x minus 1. The integral from 0 to infinity of x cubed over e to the x minus 1 dx appears, which can be evaluated using the series expansion for the denominator. By switching the order of integration and summation and substituting t equals n plus 1x, we obtain a summation of the form summation from 0 to infinity of 1 over n plus 1 to the fourth times integral from 0 to infinity of t cubed e to the negative t dt. The integral here represents the gamma function, gamma of 4, which equals 3 factorial, which equals 6. By simplifying the summation from 1 to infinity, we obtain 6 times the summation from 0 to infinity of 1 over n to the fourth, which is recognized as the Riemann zeta function. Since zeta of 4 equals pi to the fourth over 90, we can derive the final value accordingly. Combining all these results, we arrive at an expression for the total power per unit area proportional to t to the fourth. This final relation, known as the Stefan-Boltzmann law, is expressed as P equals a sigma t to the fourth, where sigma is the Stefan-Boltzmann constant. This fundamental law describes how the power radiated by a black body depends on its temperature raised to the fourth power. In the next lecture, we will briefly discuss other important examples related to the emergence of quantum mechanics. Thank you for your attention, and I look forward to seeing you then.